Hello everybody, welcome back today, and today we're going to be talking about dynamics, right? This is like, I don't know what part it is, but it'll be some part of the AP Physics series, right? And today we're going to jump to a new unit. Last time we were talking about kinematics. If you want to check that out, the link will be in the description below. But last time we were talking about kinematics. This time we're going to talk about a new unit called dynamics, which is all about forces. So, I hope you're excited, and before we get to the video, actually, I want to just say, make sure to like the video and subscribe to the channel. That really helps me out and pushes more content out to a lot of people. But anyways, hope you're excited, and let's get to it. Alright, so let's get started. So, main thing about dynamics is we're going to be talking a lot about force, right? So I'm just going to write that here, which is force, right? And now, what is force, right? So force is any kind of push or pull on an object. So I'm going to write that in red here. Push or pull on an object, right? And I'm just gonna abbreviate object as OPJ. So any kind of push or pull on an object. That is what that is basically the definition, or the you could think about it as like the concrete or the formal definition of force. Now, forces are all around us, right? That makes an object accelerate. We've seen that if you apply a force, let's say you're trying to move a box across your room, right? You're going to apply some force. You're going to push the block. For example, this was your box. You're going to push the box this way, right, to make it move that way, right? So we interact with forces all the time in the world, right? In real world examples. Now, the main thing about dynamics is Newton's laws. So there's 3 Newton's laws, right, of motion. So the first law, which this might seem complicated, right? But it's really not. Once you understand the law and what it's actually saying, then it's really easy, and it's going to help you tremendously on the problems. So what Newton's first law states is basically if an object, is moving, right? If it's moving, it's going to continue to move. So if it's moving, I'm just going to say arrow, and it's going to continue to move, right? Continue to move, and I'm just gonna write it down. So if you ever want to screenshot this or something like that to basically review again, then you know what to do. Let me just write this a little bit better. To move, right? It's going to continue to move, right? And then if an object is at rest, right? If it's like not moving, and we say rest as in it's not moving or it's not in motion. So if it's at rest, then it's gonna still be at rest, right? But the thing is, it's going to do this as long as there's no net external force. So no net external force. Now, what does that mean, right? What does that even mean, right? No net external force. So what that means is, just in simple terms, what that means is, if I don't put a force on this object, let's take this first case for example. If I don't put a force on the object, then it's going to keep moving. So what net external force means is the total force on an object. So for example, again, let's come back to our block example. If I'm pushing this is the net force on this block, and that's going to be important for second law. But in this case, if this is my block, right, and I'm just going to write block, right, this is my block, and I'm pushing it, right, the net force is this force that I'm applying right here. So what basically this law is saying is that if there's no force acting on the object, there's no external force that is acting on this object. And when we say acting, meaning like it is basically like there's no force on the object, right? There's no net external force on the object. That means it's going to continue to move if it's moving, and it's going to stay at rest if it's already at rest, right? So that's essentially, in simple terms, what Newton's first law is saying, and this is just the second part of it. Now, Newton's second law. Now, Newton's second law is basically a better way of saying what Newton's first law is, but this time it's with a formula. And this is basically the most important formula in dynamics, which is F net, or what that means is external force. So this thing that we were just talking about is equal to mass times acceleration. And that essentially tells us a lot of things, so let's talk about that. Here, we were talking about how object is moving, right? So the object is moving. That means, let's say the object is accelerating, right? It's accelerating. That means we know that there's a force, right? There's a force on the object, right? If it's at rest, that means it's 0. Or in a case where the velocity is constant, right? So velocity is constant, then we also know the force on the object is 0. The force on the object is 0, right? And force here is basically the units for force is in newtons, and obviously named after Newton's laws, right? So they're in newtons, or basically n, right? Just n. And this is also equivalent to if you were to do some dimensional analysis, which would be kilograms times meters per second squared, right? Because kilograms is standard unit for mass and acceleration is meter per second squared. So that's Newton's. So that's essentially the second law. Now you're going to use the second law to basically use that to basically just to find proportionalities and like just find different statements to like you're going to get questions like the mass increased by two times and the acceleration increased, how much the force increased, that type of stuff. So you're going to use that for a lot of proportionality, and it's also going to help you solve every kind of dynamics problem most likely, right? And what Newton's third law is a little bit confusing sometimes, but essentially what this law is saying is that if there is a force, right, there's a force, then there's an equal and opposite reaction force. An equal and opposite reaction. Oops, that is terrible. And opposite reaction force, right? And what this is saying is that if there is a force, right, so I'll actually use this law to actually explain a really common example. So let's say there's a table, right, and so just assume those are legs of the table, okay? They're horrible legs, but it's fine. Just take this for example, right? There's a block on a table, some kind of item on a table, right? If you think about it, why isn't this block falling through the ground? We know there's gravity, right? And gravity is a force, right? It's called Fg, or force of gravity, right? And we know it's a force, right? It's always acting downwards, right? Because we know that gravitational acceleration is downwards. So we know it's downwards, right? And so why isn't it falling through the ground? Well, that's because we know that there's some kind of thing holding it up, right? Which is the table in this case. Now, why doesn't it just sink through the ground, right? Because there's also a reaction force, right? There's also another force acting on the block as well. So what this law, or what this third law is saying, is that if there's a force acting on an object, there's an equal and opposite reaction force on the object, on the same object, right? It's not going to be on two different objects, because if it's on two different objects, then that's not how Newton's third law works. So okay, so like I was saying, so that Newton's third law means that obviously there's one force on an object. That means there's going to be equal and opposite reactions. So same force, same magnitude of the force, just a different direction on the object, and it has to be on the same object, right? That's what Newton's third law is saying. It has to be on the same object. It can't be like one object's acting on the block and the other one's acting on the ground. Like that doesn't work. That doesn't satisfy Newton's third law, right? So at least that isn't proven by Newton's third law. So that's essentially what the Newton's third law is saying. Now let's talk about some common forces, right? Then I'm just going to scroll down here. So some common forces, right? Let's talk about it. So we know, I'm just going to write the formula here again. We know F net, or force, or external, or net force, not external force, is equal to mass times acceleration. Now let's talk about gravity, because I already mentioned that. So what does that mean? So there's force of gravity, and what that is basically ma, right? F net, right? So that case, in this case, gravity would be acceleration would be gravity, acceleration due to gravity, right? So then that would be mg. So that's what mg is, and that's fg is. So that's basically when a block, say this case, right, it has a gravitational force downwards, which is causing it to fall down to the ground, right? So that's what fg would be, and fg is actually also equal to the weight, and so weight and mass, and so there's sometimes a misunderstanding between weight and mass. And weight is actually something that can change. It's dependent on the gravitational force. So if I'm on like the moon, for example, so Fg and weight are actually the same thing. But let's say I'm on the moon, for example, my weight, oh, that's a horrible moon. Let's say this was the moon, for example, right? This was the moon. My weight on the moon would be different from what I was on the Earth. But my mass, and this is actually a key thing, so let's just do that. So I'm going to write it, mass is not equal to weight. And what this means is, basically, my mass is always the same. So whether I'm on the moon or I'm on the Earth or wherever in the world or in the universe, my mass is always the same, but my weight is going to depend on the gravitational force of the planet. So it's going to depend on this g right here. So that's something to remember, because that's a key misconception a lot of time. And just to know that mass is not equal to weight, and mass is always going to be the same, but the weight is going to change depending on the gravitational force. So weight again is equal to mg, and actually weight's capital. Sometimes it's capital W or lowercase w. It really doesn't matter. Just be aware. Next thing is something called normal force. Alright, so let's talk about normal force. So what normal force is, let's say I have there's a block on the ground, right? It always has a weight, right? It has a weight downwards. Let's just say that's mg, right? That's the weight force. And I'll explain what these arrows are in a moment, okay? And let's coming back to normal force. What the normal force is doing is basically preventing us from sinking down through the ground. So it's basically the force from the ground on the object. So this is called Fn, or normal force of normal force, right? And this is usually equal to mg when it's a flat surface, right? Basically, it's going to be whatever your weight is counteracting, right? So, or basically what direction your ground is. So sometimes, not sometimes, but a lot of times you're going to get problems where there's an incline, right? There is an incline, and your blocks here, the normal force here is not going to be equal to mg, because remember, weight is always down. It's not like this direction, right? But normal force is in the direction of the ground, upwards. So the normal force here would be actually this direction. Why? Because this is the direction of the ground that's basically has the force on the object, and the object is tilted this way, right? In this direction, right? Not like flat, right? So that normal force would be this. So if you wanted to calculate that, you would want to take the weight, and you would find the cosine of the weight and cosine theta. And this theta, actually, if you were to do some geometry here, in fact, let me try to demonstrate. So this is actually kind of going on tangent, but this is actually an important topic, and we'll discuss this later as well, because it's going to show up in a lot of problems. But inclined planes, you're usually given theta, right? And you're given a block, right? And you know weight is always downwards. And if you wanted to find this, and you could split your weight into two like vector components, and this is when vectors are really going to matter. So here, this is like your y component and your x component. You could think of it that way. And if you were to do some geometry, like let's say we were to draw this, and then we know this angle is like 90 minus theta, right? Because this would be a right triangle. This would be a right triangle, right? And this would be 90 minus theta. So this point right there would be 90 minus theta. We know that, and that means, since this is also a right triangle, right, because we split into components x, y, so this would just be theta here. So usually you don't need to remember that, like you don't need to derive that, because after you do a lot of problems, you just automatically know. So just remember that here on inclines, for example, when you're trying to find normal force on mass on the incline, you just go weight right downwards, and then you know this is your weight cosine theta, which is counteracting your normal force, and that means your normal force would be weight cosine theta. Now that's going to depend, right, on what kind of problem it is. It could be an incline or whatever, right? So that's just what normal force is. It's the force that's counteracting or is being pushed up through the ground, right? So the ground is pushing up, that kind of thing. Now, what are these arrows, right? I was drawing these arrows, and what is that actually, right? Like the ground, and I was talking about how there's weight going down, that kind of thing. Well, this is going to be a key thing about dynamics. It's going to be there's a reason that a lot of people miss points on dynamics questions, and it's because they don't do this. And what this is, it's called a free body diagram, or I'm going to abbreviate and say FBD, which basically stands for free body diagram. What this is you basically take your object that you have. For example, let's talk about the ground example, right? The one that we had. We take the object, and then we draw all the forces acting on it. So we know, as I said, there was arrow going down. So you want to make sure that these arrows that you draw are just like vectors. You want to have good magnitudes, and you want to have them in the right direction. Sometimes you can split them into components, or sometimes you can just draw them in that direction, right? It is up to you, but I think on the AP test they want the actual direction. So if there's some kind of force going northeast like this, you would want to draw it like that. Anyways, so for the ground example, we know that weight is going downwards. So I'm just going to label that with weight, and just label your forces so you know what they are, right? Obviously. Now we knew that the upward force is normal force. And we know that normal force, we talked about, right? Normal force is equal to the weight in the ground example. So that means that I want to draw vectors that are equal in magnitude. That's what I try to emulate here, right? And that just tells me when I set up my equations later on, I can just solve for, when you're going to solve, right, using FNet, that you're going to use this. And in a lot of examples, right, you're going to see that you're going to want to set FNet in different directions. So in this case, right, for example, my FNet would be 0, and that's because obviously we know that our object isn't moving, but that's because we know that since it's not moving, acceleration so in this example, we know that FNet is 0 because we know that our object is moving, right? It's on rest, right? But we know that because if you were to calculate our FNet, which is our net force, we would usually do FNet is equal to normal force minus your weight. And why is this? Well, because in certain examples, whichever vector is bigger, right, you're going to want to subtract that to get your net force. What net force again means is the total force on your system. So I would try to get some of the difference in this, right, because one is going in the one direction, the other one is going in the opposite direction. So to get the total, just like normal vectors, like, remember, let's talk about number line, for example. Let's say you walked 5 right and then you walked 3 left. Well, your total displacement was like 2, right, from the original spot. So that's essentially what you're doing here as well. So in this case, since F net and weight are the same, that means, again, we're getting that 0 newtons, right? I'm going to write Newton there. So this is just an example of how we would use free body diagrams to our advantage. And again, you could do that for the incline one as well. Now, let's do some basic problems, okay? So we'll go into like more like example types, because we're going to go over like pulleys, right? There's going to be like blocks, and then there's going to be a pulley, and there's going to be 2 blocks. There's also just going to be a case where there's just a pulley, and then there's 2 blocks. And then obviously there's going to be inclined planes, which we also will go over next video, because I don't want to give too much information right now, because then it might just get confusing. But just know all these problems will be centered around this formula. This formula will be your friend. And just remember all the forces on the object. So let's go over some basic questions. And I don't have any like from a worksheet or something like that. I'm just going to make them up on spot. So for example, let's say again, let's go to our ground example. There's a block, right? And there's some person, and let's say this block has a mass of 4 kilograms, okay? And so let's say there's this person. Let me try to draw a stick figure. Okay, that's a horrible stick figure. It's way too far. Let's say this is the stick figure, and he's like pushing on this block, and the acceleration of this block is 2 meters per second squared. And now you want to find the net force. Well, if you want to try solving this by yourself, pause the video right here and try to solve. But I'll be going over the solution right now. And again, we're going to use, since it said it wants the net force, we're going to use our formula. Net force is equal to mass times acceleration. In this case, it's just 4 kilograms times 2, and that's just 8 newtons, right? Just a basic problem. Now let's talk about another one. So another case that I'm thinking of is, let's talk about this. So okay, so let's say there's a block, there's a ground, right, obviously, and there's some block here, and that is falling down, right? It's just falling down. We want to find its weight, right? And let's say there's no air resistance and all that kind of stuff. We just want to find the weight of the block, essentially, right? So we know that the mass is 2 kilograms. That's all we're given, and we just want to find weight. And again, stop the video if you want to solve it. I'm going to go over the solution. So the weight we know is m times g, right? Again, just a derivation of our F net formula. So that means it's going to be 2 times, I'm just going to say g is 10 here, just because I don't want to calculate it, even though it's not that hard to calculate. It's like 19.6, but this is 20 newtons, right? I rounded up to 20 newtons, right? So that's just a small, easy example. So that's essentially what I'm going to go over this video. That was all, basically, and it's just getting you introduced in dynamics and the main concepts. This was more like a conceptual video. Next video, we're going to go over a lot of problems, and we're also going to go over a little bit more on different kinds of forces, because there's also tension, which I didn't talk about, because we kind of need to know how to solve the basic like the basic incline problems and that kind of stuff to learn about tension. But really, it's just another tension, just setting up equations. So I hope you enjoyed this video. Let me know in the comment section if you think I missed anything, or if you want to see something else in the next video, or like different kinds of problems, or if you like to, even if you want to, like, if you're confused about something, if you just want an explanation, let me know in the comment section below. So again, make sure to like the video, subscribe to the channel, obviously, and I hope to see you soon.